This is the 24th video in a series that I'm making to support a course in elementary number theory. In the last video, we built up all of the tools that we needed to prove quadratic reciprocity, and we proved Gauss's theorem of quadratic reciprocity. And here we want to look at just a bunch of associated examples because we didn't have time for any of that in the last video. So let's just recall the definition of the Legendre symbol first. So A by P is equal to 1 if A is a quadratic residue mod P. It's equal to -1 if A is a quadratic non-residue mod P. And it's equal to 0 if P divides A. So I'll let you guys look up the precise definition of quadratic residue and quadratic non-residue, but it essentially has something to do with being a perfect square mod P or not. Then we had these two results, which are important, and they cannot follow from quadratic reciprocity. And that is -1 by P is 1 if P is congruent to 1 mod 4, and -1 if P is congruent to 3 mod 4. In other words, -1 is a perfect square in this case, but it's not a perfect square in this case. Furthermore, we proved that 2 by P is 1 if P is congruent to ±1 mod 8. That's 1 or 7 mod 8. And it's -1 if P is congruent to ±3 mod 8. So that's 3 or 5 mod 8. And these guys cannot be used. And the reason these two facts are so important is because quadratic reciprocity has to do with the Legendre symbol and two distinct odd primes. -1 is odd, but it's not a prime. 2 is a prime, but it's not odd. So that's why we need these two facts on their own. Okay, so let's see what quadratic reciprocity says. It says that the Legendre symbol P by Q times the Legendre symbol Q by P is equal to 1 if P or Q is congruent to 1 mod 4, and it's -1 if P and Q are both congruent to 3 mod 4. And generally, we don't use it in this shape, but we use it to rewrite P by Q as Q by P with a ±1 in there. Okay, and I want to stress here that P and Q are distinct odd primes. Okay, so let's work through a couple of basic examples first, and then we'll look at some more interesting applications. Okay, so we're going to start with this -79 by 101. So maybe the first thing that I would like to do is add 101 to the numerator. Well, it's not really the numerator, and that's because the value of this Legendre symbol is invariant under changing the top part by a multiple of the bottom part. So that's something that we proved, or maybe we heavily hinted at it in a previous video. It follows pretty quickly just from the definition of quadratic residues in the first place. Okay, so we know that this is equal to 22 over 101, or the Legendre symbol 22 by 101. Okay, and so that's just by adding 101 to the top part. In other words, 22 is congruent to 79 mod 101. Okay, but now we can factor this 22 into 2 times 11. So that'll give us the Legendre symbol 2 by 101 and then 11 by 101. Because again, if you've got a composite at the top, you can factor that Legendre symbol. That's again something that we proved in a previous video. But now we know that 2 by 101 is equal to -1. And that's because 101 is either plus or minus 3 mod 8. I'll let you guys figure out exactly which one it is. Is it 3 mod 8 or is it 5 mod 8? That should be pretty easy to calculate. So here we know that this is -1. I'll just put minus times the Legendre symbol 11 by 101. Okay. But now 11 and 101 are both primes. So maybe we'd like to use quadratic reciprocity to flip this so we've got the bigger one on top, and then we can reduce mod 11. So let's notice that this is going to be equal to minus 101 by 11. And we did not pick up an extra minus sign because 101 is 1 mod 4. So that means you can freely exchange P by Q with Q by P without a minus sign introduction. Okay, but now let's reduce this 101 mod 11. That's going to give us 2 mod 11. So that'll give us 2 in the top. So we have minus 2 by 11. But then by our rule over here, 11 is 3 mod 4. So that's going to be minus 1. So we have minus 1 times minus 1, giving us 1 in the end. So looking from the beginning to the end, we see this Legendre symbol minus 79 by 101 is equal to 1. So let's see what that really means. That really means that there is a solution to the following quadratic congruence. So x squared congruent to minus 79 mod 101 has a solution. So I'll just put a little check mark next to this to mean that it has a solution. That's because we got 1 at the end. Okay, so now let's do this one right here. So the denominator, or the bottom part of the Legendre symbol, is a prime, but the top part is a composite. It's obviously equal to 9 times 11. So we can rewrite this as 9 by 167 times 11 by 167. And you might say, well, I could rewrite that other one as 3 times 3. But look, 9 is already a perfect square. And this Legendre symbol is asking the question, are you a perfect square? But given the fact that 9 is a perfect square, like just by visual inspection, we're good to go there. We can immediately replace this thing right here with 1. And then we've just got to reduce this 11 by 167. So let's notice that they are both congruent to 3 mod 4. And so that means if we flip them, we'll pick up a minus sign by quadratic reciprocity. So this will give us a minus sign 167 by 11. And now we can start reducing the top part mod 11. So that top part is 2 mod 11. So here we've got, this is minus 2 by 11. Now we can do the same thing again. Well, look, we ended up at the same spot. So this is going to give us a minus 1 times a minus 1, which is 1. So in other words, 99 is a quadratic residue mod 167. So there is a solution to the congruence x squared is congruent to 99 mod 167. So check, that's got a solution. So in a forthcoming video, we'll talk about how to efficiently find such solutions. But right now, we just know that it has a solution. Okay, let's get rid of this and then we'll do some kind of more interesting examples. Now we're going to look at a more interesting example. So we'll answer the following question. When is 3 a perfect square modulo a prime p, which is bigger than 3? Or restated in the language of quadratic residues and the Legendre symbol is, when is 3 by p equal to 1? Notice that means that 3 would be a quadratic residue mod p. In other words, a perfect square mod p. Okay, so let's maybe notice the following first. We have 3 by p is equal to either positive p by 3 or negative p by 3. By quadratic reciprocity, we know that we can exchange the order of this top and the bottom. We may pick up a minus sign depending on whether these parts are congruent to 1 or 3 mod 4. Well, we know 3 is 3 mod 4. Obviously. So all of this switching hinges on whether or not p is congruent to 1 or 3 mod 4. Well, so let's notice we do not pick up a minus sign if p is congruent to 1 mod 4. And we do pick up a minus sign if p is congruent to 3 mod 4. Okay, so that's how we can switch our 3 by p with our p by 3. Okay, so now let's move on to answering whether or not p by 3 is plus or minus 1. And that's actually a little bit easier than you might think. And I'll write it out, and then we'll discuss why this is the case. So p by 3 is equal to 1 if p is congruent to 1 mod 3. And it's equal to negative 1 if p is congruent to 2 mod 3. So since we're working mod 3 here, we only really need to look at two numbers, 1 and 2. Notice since p is prime, it cannot be 0 mod 3. But then just by a quick calculation, it's obvious that 1 is the only perfect square modulo 3. And so that means you only get a 1 here if p is 1 mod 3. Again, 2 is not a perfect square mod 3. Okay, great. So now we somehow want to put these two things together. Great. So notice if we're getting a 1 from the output of this, then we need to get a 1 in front of here as well. And if we're getting a -1 from an output from this, we need to have a minus sign from the output of this. Okay, so let's maybe look at what's happening with this peach underlined stuff first. So we have 3 by p is equal to 1 if the following two things happen. P is congruent to 1 mod 4. That's from this right here. And P is congruent to 1 mod 3. That's from this one right here. But it's pretty easy to put those two together. You know, if this were a little bit more complicated, we would have to use the Chinese remainder theorem, but we can just do this by inspection, and we'll see that this means P is congruent to 1 modulo 12. Okay. But then let's see what happens when we put the purple stuff together. We'll see that 3 by P is equal to 1 if P is congruent to 3 mod 4 and P is congruent to 2 mod 3. So that means we pick up a minus sign in both of these cases, which clearly cancel to a plus sign. Okay, but let's put those together. Again, if this were more complicated, we could use the Chinese remainder theorem, but it's pretty easy to do with just visual inspection. And we'll see that here we get P is congruent to 11 mod 12. Okay, so that means we can answer our question. When is 3 a perfect square modulo a prime? Well, when that prime is congruent to plus minus 1 mod 12. Here I'm using minus 1 mod 12 for 11 mod 12. That means in all of the other cases, like if it's 5 mod 12 or 7 mod 12, it will not be a perfect square. So it's actually not a terrible idea to keep facts like this in a list. So we could add it to our list over here. So we know -1 is a perfect square in this case, 2 is a perfect square in this case, and now we know when 3 is a perfect square. Okay, so let's clean this up and we're going to look at some more examples. Okay, we're going to finish this video off with one last application of quadratic reciprocity. But before we dive into that, which I've called this a theorem, I want to give you guys a warm-up problem. And I'm giving you this warm-up problem now because we're going to use this result within the proof of this theorem. So this follows pretty similarly to our last example. It's just you do it with these two guys right here. And that is show that -2 by P is 1 if P is congruent to 1 or 3 mod 8. And it's -1 if P is congruent to 5 or 7 mod 8. So in other words, -2 is a perfect square in this case up here, and it is not in this case down here. Okay, so what theorem are we going to prove? We will prove that there are infinitely many primes that are congruent to 3 mod 8. In other words, they are of the form 8k plus 3. Okay, so let's get into the proof. So we're going to do this in the standard method of a proof by contradiction. So we'll start out by supposing that P1 to Pn are all of the primes of this given form. So let's say all of the primes of the form 8k plus 3. In other words, they're all the primes that are congruent to 3 mod 8. Now we want to work towards a contradiction. So what will we contradict? Well, we will contradict this assumption that there are only finitely many primes, and that'll be a problem. Okay, so now we want to build some objects out of these primes that we can exploit with quadratic reciprocity, again, to build that contradiction. So let's set x equal to the product of these primes. So P1, P2, all the way up to Pn. And then let's set n equal to x squared plus 2. And now before we keep going, I want to notice that this number x is congruent to 1 or 3 mod 8. You might say, well, how do we know that? Well, that's because if you multiply things that are 3 mod 8, they loop between being 1 mod 8 and 3 mod 8. Notice 3 times 3 is 9, which is 1. And so this is 1 mod 8 if this number n is even, and this whole number is 3 mod 8 if this number n is odd. It actually doesn't matter the parity of this number for the rest of our argument, but all we really need is that x is congruent to 1 or 3 mod 8. But notice that that tells us that x squared is congruent to 1 mod 8. Again, because 3 squared is 9, which is 1 mod 8. But now putting that together with this number 2, that tells us that this number n is congruent to 3 modulo 8. And this actually is a pretty important fact for kind of the end portion of the proof, but it's really nice to notice at this stage because we've just introduced x and n. Okay, great. So n is a natural number, that's a fact. And so that means it has a prime divisor. So let's suppose that p is a prime such that p divides n. So for any natural number, you can find a prime divisor, I guess, except the number 1, but this is clearly larger than 1. Okay, but notice that if p divides n, that tells us that n is congruent to 0 mod p. It's like the definition of divisibility and congruence. But plugging in this value for n, this x squared plus 2, and moving some things around, we see that x squared is congruent to negative 2 mod p. In other words, negative 2 by p is equal to 1. Well, negative 2 is a quadratic residue, but that means its Legendre symbol gives us an output of 1. But now let's notice that that means p is either congruent to 1 or 3 mod 8. And that's by this warm-up exercise up here. But now since this p was an arbitrary prime divisor of n, that means that all prime factors of n are congruent to 1 or 3 mod 8. Great. Now I want to argue that at least one of them is congruent to 3 mod 8. I'm just going to write that down now. At least one, I'll call it Q, is congruent to 3 mod 8. And I'll explain why verbally. You guys can write this down if you need to. Well, if this were not the case, in other words, if they were all congruent to 1 mod 8, then when we took their product, we would get a result that was 1 mod 8. But we know our result should be 3 mod 8 by this thing over there that's in green with the red box. So that means they cannot all be 1 mod 8, so at least one of them has to be 3 mod 8. So let's see what we've got. We've got the existence of a prime that is 3 mod 8 that divides n. So that's going to pose a problem, but we don't have quite enough room to show that problem here, so let's maybe clean up the board. I'll summarize what we've got, and then we'll finish it off. So now we're ready to finish the proof of this theorem off, which will finish this video off. So let's just recall that we're working by way of contradiction. We suppose there were only finitely many primes of the form 8k plus 3, and then we formed this number. So I've taken some of the parts out of it, but this is the number that we were working with. Called it capital N, and it was the product of all of these primes up here squared plus 2. That meant that it was congruent to 3 mod 8. We discussed why on the last board, and we discussed why that was important on the last board. And the conclusion of the last board was that there is a prime Q that divides n such that Q is congruent to 3 mod 8. But now, along with our assumption that this list P1 to Pn is all of the primes of the form 8k plus 3, that means that Q equals Pi for some I that's between 1 and n. Well, why is that? Well, we've got a prime, which is 8k plus 3. In other words, it's 3 mod 8 that divides n. But all of the primes that are 8k plus 3 come from this list. Okay, so now that's really going to cause a problem. So now let's notice these two facts. So now we have Pi divides n. Well, that's because Q is equal to Pi, and we said that Q divided n. And Pi divides this number right here, P1 up to Pn squared. That's pretty clear because Pi is one of the factors in there. But that means that Pi divides the difference of these two. We've used stuff like this a bunch of times. If we have something dividing two objects, it must divide the linear combination of those two objects. Well, in this case, if we take this difference, we see that Pi divides 2. Notice 2 is equal to n minus this. But is there a prime that is 3 mod 8 that divides 2? No, there is not, because the only prime that divides 2 is equal to 2. Obviously, because 2 is prime, but 2 is not congruent to 3 mod 8. So we've reached a contradiction. What did we contradict? We contradicted this assumption up here that this list P1 up to Pn was all of the primes. So this must not be all of the primes. So there must be infinitely many primes. And that's a good place to stop.